Title of the experiment is Determination of Cell Constant of a Conductivity Cell and Estimation of Concentration of a weak acid and strong acid in a mixture of acids by conductometric titration with a strong base. Aim of the experiment: to determine cell constant of a conductivity cell and to determine the concentration of a weak acid and a strong base in a mixture by conductometric titration with a strong base. There are two parts in this particular experiment. Let us discuss in detail about the theory for part A. The first part is determination of cell constant of a given conductivity cell. An electrolyte is an electrically conducting medium in which conductance is because of presence of ions. Mainly there are two types of conduction. One is electrolytic conduction, other one is electronic conduction. From a macroscopic point of view, if you look at this conductance, ionic conduction in solutions, that is electrolytic conduction, is similar to electrons or holes conduction in solids, that is electronic conduction. Conductance is a reciprocal of resistance and it's a measurement of an ability to conduct electricity. It depends upon concentration, mobility, valence and temperature of ions present in the solution. Experimentally measured conductance of a solution is that of a certain volume of a solution contained between the electrodes of a conductivity cell. Conductometer measures the resistance of a solution between two electrodes and converts it into conductance values. We know that G is inversely proportional to R, where G is observed conductance, that is in Siemens, and R is nothing but resistance. Specific conductance is the conductance of the electrolyte solution normalized to unit length and unit area of cross section of the electrode at a specific temperature. Specific conductance K, kappa, is given by K is equal to L by A into G, where L is distance between the electrodes, A is area of the electrodes and G is observed conductance. If you replace this G with 1 by R, we know that G is equal to 1 by R. So, kappa K is equals to L by AR. The cell constant is given by C is equal to L by A. Kappa K is equal to L by AR. If you replace this L by A with C and 1 by R with G, then kappa K is equal to C into G. But we want to find out cell constant C, so that C is equal to K by G. If you know the K value, then by measuring observed conductance of a solution, easily we can find out cell constant. Conductometric titrations are very precise when compared to the classical method of analysis. Further, in case of dilute solutions and precipitation reactions, the estimation can be carried out with accuracy. The titration of weak acid with a weak base cannot be done by conventional methods, but it can be done conductometrically. A titration in which equivalence points are measured by measuring conductance of a solution, then we call it as conductometric titration. Conductance of a solution depends on number of ions, charge on the ions, temperature, and also on the mobility of the ions. During the course of titration, the conductance of the solution changes. Hence, there is a sharp break in conductance volume curves. This break corresponds to the equivalence point. In a mixture of strong acid and a weak acid, the strong acid undergoes complete dissociation as it is a strong electrolyte, and the weak acid remains almost undissociated. When a mixture of HCl and acetic acid is titrated against NaOH, the HCl is consumed first by the base. After neutralization of strong acid is completed, then only the weak acid is neutralized. When we titrate acid mixture, that is HCl and acetic acid versus NaOH, what happens is this HCl first reacts with NaOH, forms NaCl and water. Now, this more mobile H plus ions are replaced by Na plus ions, hence conductance decreases. Again, now when all this HCl in the acid mixture is completely exhausted, only acetic acid is there in the solution. Now, if you further add NaOH from the burette into the solution, what happens is this NaOH reacts with acetic acid, forms sodium acetate and water. Actually, the sodium acetate is also a strong electrolyte, hence there is slight increase in the conductance. When all this HCl and acetic acid completely exhausted in a solution, then if you further add NaOH from the burette into the solution, conductance values increases. That is because of OH minus ions from NaOH. Plot a graph of conductance versus volume of NaOH. If you look at the graph, there is a gradual decrease in the conductance values. Okay, that is because high mobile H plus ions are replaced by Na plus ions. Again, there is slight increase in the conductance values. That is because of sodium acetate, which is a strong electrolyte. Then there is large change in the conductance values. That is because of OH minus ions from the NaOH. Okay, now, the point of intersection of first and second line is nothing but neutralization of HCl, whereas point of intersection of second and third line is nothing but neutralization of weak acid, that is acetic acid. The apparatus required: you need distilled water, spatula, 10 ml pipette, 200 ml volumetric flasks, 2 beakers, conductometer which has conductivity cell, burette, small funnel, chemicals required for this: potassium chloride salt, acid mixture, that is HCl and acetic acid mixture, sodium hydroxide. There are two parts in this particular experiment. First part is determination of cell constant of a given conductivity cell. For that, you need two different concentrated KCl solutions, that is 0.1 molar and 0.01 molar KCl solutions. To prepare 0.1 molar KCl solution, first take a sheet of paper, fold it like this. After folding the paper, keep it on a panel like this. Then press tear button. Now the paper weight is 0. Then transfer KCl salt onto a paper like this. After transferring the salt, close the doors, both the doors. Then, now the weight of the salt is 0.745 grams. Then take out the salt like this. Then transfer onto a funnel. After weighing the salt, take 100 ml volumetric flask. Then take a small funnel and keep it on the flask. Then transfer salt carefully onto the funnel like this. Make sure that all the crystals are completely transferred onto the funnel. Then add distilled water like this. Make sure that you are transferring all the crystals into the flask. After adding water, take out the funnel. Then swirl the flask. Then add one more portion of water. Then swirl the flask to dissolve KCl crystals. Then add water just below the mark by using this wash bottle. Then for the final makeup, you have to fill the burette with distilled water, then make up to the mark by using distilled water. We have filled water just below the mark by using distilled water. Now let us make up to the mark by using distilled water. First we have to fill this burette with the distilled water, then add slowly drop by drop. Now you can see that we have added water up to the mark. After that, close with the stopper. After adding water up to the mark, tilt the flask and shake the bulb 2-3 times for uniform concentration. Now we have prepared 0.1 molar KCl solution. By using this solution, we have to prepare 0.01 molar KCl solution. For that, take one more 100 ml volumetric flask. For the preparation of 0.01 molar KCl solution, let us pipette out 10 ml of 0.1 molar KCl solution by using 10 ml pipette. After pipetting the solution, transfer this solution into another 100 ml volumetric flask. So to transfer even a last drop which is there in the pipette, just touch the tip of the pipette to the bottom of the flask like this, so that all this KCl is completely transferred into 100 ml flask. After transferring 10 ml of 0.1 molar solution into 100 ml volumetric flask, add distilled water to the flask. Then swirl the flask. Again add one more portion of distilled water. Then swirl the flask. Then add water just below the mark by using wash bottle. Again, for the final makeup, fill the burette with distilled water, then add drop by drop to make up to the mark. After that, close with a stopper, then tilt the flask, shake the bulb for uniform concentration. Now we have prepared two different concentrated KCl solutions, that is 0.1 molar KCl solution and 0.01 molar KCl solution. This is conductivity cell which has two platinum electrodes. This is one platinum electrode and this is another platinum electrode. This conductivity cell is connected to conductometer like this. After preparing 0.1 molar KCl solution, take a 100 ml beaker, then keep the magnetic pellet inside the beaker slowly. Then transfer this 0.1 molar KCl solution into this 100 ml beaker slowly. You can take roughly about 40 to 50 ml of KCl solution. Before measuring conductance of 0.1 molar KCl solution, let us rinse this electrode with a distilled water like this. After rinsing the electrode, take 0.1 molar KCl solution and immerse this conductivity cell inside the solution and make sure that both the platinum electrodes are completely immersed inside the solution. Then note down the conductance value. After measuring conductance of 0.1 molar KCl solution, let us clean the beaker with distilled water. Then after cleaning the beaker, then transfer magnetic pellet inside the beaker. Then transfer roughly about 40 ml of 0.01 molar KCl into 100 ml beaker. After that, rinse the conductivity cell with distilled water. Then immerse conductivity cell inside 0.01 molar KCl solution. Magnetic stirrer is on. Now note down the observed conductance. Let us move on to second part of this experiment. For that, first you need to take 2 burettes and fill one burette with acid mixture, that is HCl and acetic acid, and another burette with sodium hydroxide solution. After that, transfer 30 ml of acid mixture into a beaker. First, rinse the conductivity cell with distilled water like this. After that, immerse this conductivity cell inside acid mixture. Then note down the conductance values without adding NaOH solution. Initially conductance values will be high, that is because of high concentration of H plus ions which is there in the solution. Then add 0.5 ml of NaOH from the burette. Actually stirrer is already on, so you have to make sure that you are mixing solution properly. After that, add 0.5 ml of NaOH. Then continue the stirring for about 20 seconds. Then note down the change in conductance values. Actually conductance values decreases because high mobile H plus ions which are there in the solution are replaced by low mobile Na plus ions which are there from the NaOH solution. After that, continue the addition of NaOH from the burette into the acid mixture solution. Actually conductance values gradually decreases, then there will be slight increase in the conductance values, then there is rapid increase in the conductance values. As you know, there are 2 parts in this particular experiment. Part A is nothing but determination of cell constant of a given conductivity cell. Actually, cell constant value is already there on the conductivity cell, you can check it. However, see, we have prepared 2 different concentrated solutions, that is 0.1 molar KCl and 0.01 molar KCl solutions. And also we measured observed conductance for 0.1 molar and 0.01 molar KCl solution. And if you look at the tabular column, we have given specific conductance values for both 0.1 and 0.01 molar KCl solutions. Now, you know the formula C is equal to K by G. So, substitute those values and find out cell constant for 0.1 molar KCl solution and 0.01 molar KCl solution. Take average of those two, you will get average cell constant which is in centimeter inverse. Part B, the estimation of amount of HCl and acetic acid present in given acid mixture. Okay, let us move on to the tabular column. Now, initially measure conductance of a given acid mixture without adding NaOH. Initially it will be high. Then add 0.5 ml of NaOH, note down the conductance value. Again add 0.5 ml of NaOH, note down the conductance values. You can see there is a decrease in the conductance values. You have to add NaOH in 0.5 ml increments. So there is a gradual decrease, slight increase and rapid increase in the conductance values. This completes your first experiment.